Okay, so this is the second of 3 videos on chemistry review, and I would suggest that if you haven't watched the first video that you go back and you do that and you complete the worksheet. So what are we looking at here? Well, we in chemistry use symbols to represent specific elements on the periodic table. In this case, the symbol Na represents sodium. And the reason we use these sort of short forms is just to kind of, it makes writing out the chemical formulas a lot more simple. Okay, sort of like, when we use scientific notation to represent large numbers, we're going to use chemical symbols as just an easier way to convey information about elements and compounds. Okay, so what is a chemical symbol? It's just an abbreviation of the name of an element. You probably already know that, but there's some details around this that I think are important for you to remember. So here we go. So only the first letter, and this is just by convention. These are the rules that, an organization called IUPAC decides. Only the first letter is capitalized. Some elements only have one letter. So for instance, if this were nitrogen would just be N, right? Whereas, this A right here, in this case, there are 2 letters, but the second letter is always lowercase. Okay, so the first letter is capitalized, the second one isn't. And this just reduces confusion between certain elements and certain compounds. So for example, if we have CO with the O capitalized, well, we know O can represent the element oxygen. So there's a difference between if I write this as capital C, capital O, versus capital C, little o. Because the first case, I have carbon monoxide, right, which is a deadly poison. And the second, I have the element cobalt, which is a metal, right? And so, there's a difference there. They have different chemical and physical properties that are very important for a reader to be able to distinguish. And so the convention is, that's why we have that convention, okay? And in fact, here on the periodic table, right, I have cobalt. Okay, whereas over here, carbon monoxide is composed of the element carbon and the element oxygen over here. Okay, so just when you're writing your chemical formulas out, that's a way to be clear about what you're trying to represent. So while we're on the topic of the periodic table, let me remind you of a few details. I would strongly encourage you to print out a copy of this periodic table, which you should be able to find in the week plan as a separate document, and to have that in front of you at all times when we're working through concepts in this unit. It's going to be incredibly important for you to have this as a resource. So I'm going to start off with some basics from grade 9. Which are that you can see clearly that, most of the elements are colored in blue. Oops, I'm going to go back here. Others are colored in pink. And then, these ones here in the middle, sort of between the pink and the blue, are colored in green. Okay, the legend over here will remind you that we have the blue are the metals and the pink are the non-metals. Okay, and then the metals and the non-metals are separated by this, what we often call the staircase line. And all along the staircase line, we have these elements called metalloids, which are sort of in between being metals and non-metals. They have varying properties of metal and non-metals, which is why we call them metalloids. Okay, so what's important to know right now is that this staircase line is going to divide the metals, which are on the left-hand side, from the non-metals, which are on the right-hand side. Now, that's another thing to notice that, not all students notice, so I'm just going to mention it, okay? The symbol for the element is there, obviously. This is a legend, by the way, okay? And that you have the solids in black, the gases in red, and the liquids in blue. Okay, so you can also see that most of the elements at room temperature, and this is all based on room temperature, are solids, right? But we have a few of the non-metals. Most of the non-metals are gases. We have a few non-metals that are solids here, okay? But we have very few elements at room temperature that are going to be in the liquid state. So bromine is our non-metal that is a liquid at room temperature, and mercury is our metal that is liquid at room temperature. All right, so there we go. Just a quick reminder of how to locate metals and nonmetals on the periodic table. That is going to be really important for us. Okay, so next on to chemical formulas. Now, in grade 10, what we extend upon from grade 9 is the idea that chemicals will react together to form new materials. And so, in fact, the unit is called chemical reactions because we're going to be introducing you to chemical reactions this year. So, what is a chemical formula? It's when we take the symbols of the elements and we, combine them together to represent some kind of a compound or an element. Okay, so for example, the chemical formula for water, you probably already know. What is it? H2O. And so when we write that chemical formula out, we're telling the reader that in every particle in water, we have 1 oxygen for every 2 hydrogen atoms. Okay, that is what makes up water. And if I were to change any of these proportions in here, as we talked about in the first video, then that makes it a different substance. Even just adding a 2 right here makes this H2O2, which is not water anymore. That's hydrogen peroxide, which is very different chemical and physical properties. Okay, so another example is a chemical formula for calcium hydroxide. And in this formula, they're telling me how many calciums there are for every oxygen and every hydrogen. So at this point, I'm going to help you learn how to count your atoms. And there are examples in the worksheet that will further this, but that is going to be very important later on the unit that you be able to balance chemical reactions, and you need to be able to know how to count formulas well. So count the atoms in a formula well. So I want you to think about this 2 out here, almost like we would consider it in math as being outside the brackets of something inside. So maybe I'm going to just write something out here so that you can maybe see that. Okay, so if I had in math, I had let's say 2 times x plus 3, I know that 2 out there is going to have to get distributed to, both of these in here, right? Okay, in the same way, when I look at a chemical formula, this 2 that is out here has to get distributed. That's telling me that there are 2 oxygens in this formula and there are 2 hydrogens in this formula. But this 2, notice, is outside the bracket, so it actually doesn't apply to calcium at all. So in this formula, I would say that I have 1 calcium, I have 2 oxygens, and I have 2 hydrogens. Okay, if that's an idea that doesn't make sense to you, make sure you reach out and we can do more practice so that you understand this idea thoroughly. Okay, so I'm going to go back now and talk to you about the next little bit. Okay, so we're going to move on to digging really deep into the structure of an atom. You probably remember this, I want to say, from hopefully elementary school. Elementary school, a lot of these ideas from grade 9 we introduced to you as well, and then we just kind of extend upon them. So what am I looking at here? I'm looking at the, what we understand as an early model of the atom. And so what do we call this region right here? What do we call that region in an atom that's sort of at the middle? Well, hopefully you are thinking about the nucleus. And so we have in an atom, we have the nucleus, which has, particles that are positively charged and particles that have 0 charge. And then around in these rings, which in early years you're going to learn we call them orbits, but later on we're going to talk about them as energy levels. Okay, and we have these negatively charged particles existing in those energy levels. Now, take a minute to try to remember, what do we call these positively charged particles? What do we call these 0 charged particles, and what do we call these negatively charged particles? Hopefully you were able to associate the negatively charged particles as being electrons, the positively charged protons and neutrons existing in that nucleus. And so that brings us to the next part, which is our standard atomic notation, which is going to be very much related to the structure of the atom. So this, to be clear, is this symbol right here is not what we see on the periodic table. This is the symbol that we would use, let's say, in a paragraph or in a lab report to maybe convey information about the number of protons, neutrons, and electrons in an atom. Okay, and so that, you know, this is again what we call standard atomic notation. Okay, and this is the way that no matter what country you live in the world, you're going to understand this symbolism and what the values that are in the place of A and Z mean. Okay, so without further ado, let's remind you of that. Okay, so we would have normally a number here in the place of A. A is meant to be like a variable, right, that we can input specific values for. And if we were to put a specific value there, that value would represent what we call the mass number of an atom. Okay, and the mass number represents the number of protons plus the neutrons just combined together. Whereas this value down here in the place of Z is what we would call the atomic number. Okay, and the atomic number typically represents the number of protons in an atom. Protons are kind of like the DNA of an atom. They represent, like, you know, we define an element based on the number of protons we find in that nucleus. Okay. However, if we're dealing with a neutral atom, then we know the number of positive and negative charges are going to be the same, and so we can often say that that can also represent the number of electrons that we have if the atom is neutral. Okay. Let's do an example to help you remember this, or to clarify if you're not 100% sure about what's going on right now. So let's practice. What I want to do now is I want to practice this with an actual diagram of a particular element. In this case, I've chosen fluorine. Okay. And this, you'll remember, is called the Bohr-Rutherford diagram, which we're going to review in a second here. Okay, so I've already input all the data into this diagram of a fluorine atom for you. And all we have to do is kind of just plug in the values to get the standard atomic notation for fluorine. And so I know that the number of protons plus the neutrons, I can get that by looking at my nucleus. Well, how many protons do I have? 9. How many neutrons do I have? I have 10. So 9 plus 10 is going to give me 19. And now to get the atomic number, I simply need to look at the number of protons. So notice I didn't really look at the electrons. I'll look at that in a minute. Okay, but the number of protons are 9, which means I just need to go over here and I need to put a 9 in. Okay, now I can check to see if this is an atom of fluorine, if it is electrically neutral, by checking to see if the number of positive protons are the same as the number of negative electrons. Let's do that. Well, I've got 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So since I have 9 electrons as well, I know that this is representing a neutral fluorine atom. Okay, now the last thing I need to do is I would need to change the value here of X and make this the symbol for fluorine. So let me just kind of bring this all together. So the standard atomic notation for fluorine would be, I would put that F there. Oops, I have no idea what I just did there. Let's try that again. I would go F, and I would put my 19 up here, and my 9 down here. And then I'm done. Okay, let's practice that a bit. Okay, all right. So remember that I started you off with the particular element there that's Bohr-Rutherford diagram drawn out. But at the end of the day, you need to be able to get that Bohr-Rutherford diagram on your own. And so let's look at the building blocks before that, and then we'll put all the pieces together so that you can write out the standard atomic notation for a particular element. Okay, so to get the information you need to do that, you're going to be looking at the periodic table. Okay, so again, hopefully you have that printed out in front of you. Okay, so, first of all, in the upper left-hand corner, for each element, you're going to see a number. That number is the atomic number. And remember, the standard atomic notation is not how we write it. It's not how it's represented on the periodic table. In fact, it's flipped. Okay, so the atomic number you're going to find in that upper left-hand corner. So for example, this atomic number right here for iron is 26. That's telling me that it has 26 protons. Okay, I'm going to, remember, so there's my atomic number. Now I also need to have the mass number. Now the periodic table doesn't give me the mass number directly. It gives me this thing called the atomic mass, and it has decimal places. So to get the mass number, what I need to do is I need to take that atomic mass value and round it to the nearest whole. Okay, so when I see 55.85, that 8 tells me I need to round up, and so the mass number that I would use for iron would therefore be 56. So to summarize, let me write out the standard atomic notation for iron. So iron would be Fe, writing out its symbol. Now remember, its mass number I'm going to get by rounding off that atomic mass to 56, and it goes on top. Okay, and the bigger number is always going to be the one that goes on top, and if that helps you remember, great. So then on the bottom, I need to put that atomic number, which represents my number of protons, 26. And there, I'm done. That is the standard atomic notation for iron. Okay, let's take a look at the next slide. Okay, so what I want you to do is I want you to try to write out the standard atomic notation for each of these particular elements. Okay, and then what I want you to do is to also tell me how many subatomic particles, that means tell me how many protons, neutrons, and electrons are in each of these elements based on that standard atomic notation. And so I would suggest if you're struggling with this, maybe go back and watch the last little example that I gave with iron to help you better understand and give these examples a go. So I've just moved to a Jamboard just to facilitate writing some of this out. Okay, and so if you tried this, hopefully you're a little bit confused, maybe just watch to see how some of these pieces fit together. So first of all, when I'm writing out the standard atomic notation, then I want to make sure I include the symbol of the element in the place of X. The mass number goes A, and then the atomic number goes in the place of Z. Okay, so I'm going to start by writing out my calcium, my atomic symbol. I'm going to look for my mass number by looking at the atomic mass, and I'm going to round that to the nearest whole, and the rounding that gives me 40. So we get 40 here. Next, I'm going to look at my atomic number, and so my atomic number is this value here up in the left-hand corner on my periodic table, which tells me the number of protons. So hopefully you did okay with that. You might have been confused a little bit about how to go ahead and get these subatomic particles. So let me break that down for you. So we're looking for the number of protons. We're looking for the number of electrons. And we're going to be looking for the number of neutrons. And so, when I look at this atomic number right here, remember that that atomic number represents the number of protons. And so by knowing that the atomic number is 20, I know that I can simply just put in 20 for my number of protons. Now my number of electrons, remember in the question I specified that we're going to assume that this is a neutral particle. And so if this is a neutral atom, that means that the number of protons and electrons have to be the same, right? The number of positive charges have to equal the number of negative charges. And so I'm going to say that there are also 20 electrons. Now, the last little bit is, well, how do I get my neutrons, right? How do I get those? And so the way that I do that is by going ahead and saying, well, I know that this 40 right here is a result of my protons plus my neutrons. So if I take away the number of protons, right here, then I can get my neutrons. And that's what you have to do. So it's set up so nicely here. All I have to do is say 40 minus 20 gives me 20 neutrons. Hopefully you remember this from last year. And that will give me my 20 neutrons. So now I have the number of protons, electrons, and neutrons for this atom. Okay, let's try the next one. So here is argon. And again, if you struggled with any part of the last example, I'm going to strongly encourage you to, to invest in trying to understand this. Don't let me spoon feed you this. Stop the video, give it a try on your own. Okay. So now when I look at this, argon on the periodic table, then I can see that I'm going to have its symbol as Ar. I'm going to look for its mass number by looking at the atomic mass, rounding 39.95 to 40. And coincidentally, it's the same thing as we saw with calcium. Okay, maybe not so coincidentally. And then what I'm going to do to get my atomic number, which goes down in this spot, is I'm going to look up here in the upper left-hand corner to give me my 18. Okay. Now, so there I've got my standard atomic notation. Okay, the next thing that I'm asked to do in this question, and that's going to be really important for us when we start to do our Bohr-Rutherford diagrams, which is I need to know how many protons, how many electrons, and how many neutrons I have in this atom. And so the number of protons I'm going to get from that atomic number, right? That's the number of protons. So it's 18. Now again, in the question, I specified that this would be a neutral atom. And so I know that the number of electrons are going to have to equal the number of protons because of that neutrality. So the last thing I need to get are the number of neutrons. And so the number of neutrons I get by just simply saying my mass number minus my atomic number. Okay, I'm going to do a subtraction here, and that's going to leave me with 22, which means that this particular atom has, every atom of argon has 22 neutrons in it. Okay, so I would suggest to you that if you struggled with that is something to reach out to me and ask for help at this point via our Zoom meeting or via email, and I'll be happy to practice until you consolidate this because it's very, very important for what we do moving forward. Okay, so what am I looking at here? Well, it looks like I'm trying to build a model of an atom, and I've already talked about this in this video already. Hopefully you remember that when we talk about a Bohr-Rutherford diagram, basically what you're doing is you're trying to create a two-dimensional depiction of the structure of an atom by kind of outlining where the number and the position of the protons, neutrons, and electrons are in that diagram. So, couple quick reminders. Okay, we have our protons and our neutrons in the middle in that nucleus. Okay, but then we start to fill electrons into these energy levels, right? And so I've drawn out 3 energy levels here, but not all atoms have 3 energy levels. Some have more, some have less. But there are certain rules to how many electrons can fit into each energy level. Not sure if you remember that or not, but we're going to go through this. So take a minute to try and see if you can remember. Well, how many electrons go in that first energy level right there, right next to the nucleus? Well, that first energy level can hold a maximum of 2 electrons. What about the next energy level? Well, the next energy level can hold a maximum of 8 electrons. And I'm going to talk to you about how we fill those in, just to remind you. Okay, and then in the third energy level, we can fit up to 18 electrons. But, for the purposes of grade 10 science, we're going to just work up to calcium, okay, element number 20, in which case we're going to have 8 electrons in that third energy level, and thereafter, after calcium, we get into the transition metals, and that's where things get kind of wonky, and so we can't make predictions in the same way. Okay, so for our purposes, this is kind of how it's going to go, and then everything thereafter. Okay, let's start to practice this. We know now how to get protons, neutrons, and electrons from the periodic table. But now what we're going to do is we're going to use that information, we're going to extract it, and start to build these Bohr-Rutherford diagrams. Okay, so let's start with nitrogen. So when I look at nitrogen, I can see that I have all the information that I need in order to get the number of protons, neutrons, and electrons. Right, so take a minute to see if you can extract that information, and then we'll double check it together. So the atomic number up here is what's telling me that I have 7 protons. I'm going to assume for now that everything is neutral, and that's going to mean that I have 7 electrons, right? Those positive and negatives are going to have to balance. Okay, now if I round this value to a 14, that becomes my mass number, right? So 14 minus 7, right? My mass number minus my atomic number is going to give me my number of neutrons, and that's going to give me also 7, coincidentally, in this case. Okay, so now I can start to build my Bohr-Rutherford diagram. So I'm going to draw out a nucleus. And remember that my protons and my neutrons go there. So I have 7 protons and 7 neutrons. And so there, I'm just going to put them in. And now what I need to do is I need to start building my Bohr-Rutherford diagram by adding electrons. And so this diagram is telling me, or this outline here is telling me that I have 7 electrons to work with in nitrogen, no more, no less. So I'm going to create that first energy level, and I'm going to place 1, 2 electrons in that energy level. Okay, now notice that I've placed them opposite each other. Okay, they're not right next to each other. That's just by convention how we want to do things. Okay, now so I've used up 2 of my 7. So that means I've got 5 left. So let's create another energy level, and we're going to build that Bohr-Rutherford diagram. So again, I've got 1, 2. So I've got to put in 3. And we don't group them together. We go all around the world in all 4 quadrants before we start to double up. So I've got, let's start again. 1, 2, 3. And I've got 4, 5, 6, 7. And so I've added all the electrons that I need based on the number that are outlined on the periodic table. Okay, so notice I didn't double up until I've gone and filled each of the 4 quadrants. That's just by convention how we create that Bohr-Rutherford diagram. Okay, now I could have started here and then gone all around and then doubled up in another spot. That would be totally fine. Okay, so at this point, what I want you to do is I want you to try this next example, potassium. And again, this is going to be critical to your understanding of what we do moving forward. So you need to invest in learning this. So give it a try on your own and resume the video when you are ready, and we'll take up the answer. Okay, so I've gotten a bit of a head start here by grabbing the information from a periodic table about the number of protons, electrons, and neutrons. And then what I've done is I've created my nucleus with my 19 protons and my 20 neutrons. And so I've got 19 electrons to place in these orbits and these energy levels. And so I'm going to start by creating my first energy level and putting my 2 electrons that go there. Okay, so I've got 17 more to go. So I've got 2, I'm going to go 3, 4, 5, 6, 7, 8, 9, 10. But now I've filled up that second energy level, can only hold 8. So I've got 10 electrons used. I'm going to create another orbit or energy level and keep going. So 11, 12, 13, 14, 15, 16, 17, 18, And so I've got 19 electrons to use, but I've filled up this third energy level. So I just simply need to create another orbit or energy level and put that last electron in there. So hopefully if you made any mistakes, that clarified it for you. If it didn't, very important for you to reach out. One last example, just in case you need to consolidate, feel free to, pause the video and try sulfur. So I've gone ahead and I have, drawn out the information from the periodic table here. So double check those values for yourself. And I've created my nucleus with the protons and the neutrons in it. So now I'm going to start to fill those 16 electrons into their energy levels. So putting 2 in the first energy level, building another energy level because 2 is the max in that first orbit. Now, so I've used up 2. I've got 3, 4, 5, 6, 7, 8, 9, 10. Okay, for a total of 8 in that second orbit. Okay, now I've used up 10 and I need to use up 6 more. So I'm going to need to create another energy level. So 10, 11, 12, 13, 14, 15, and finally 16. Okay, so there will be additional practice for you on the worksheet. Make sure that you double check your answers with the answer key to ensure that you're on the right track. That's it from there. So what I want you to do is I want you to stop this video now. We did a lot of information and we covered a lot in that last little in this video. So I want you to stop and consolidate these ideas by working through practice questions numbers 1 to 4 on the chemistry review sheet. Check your answers and invest in really understanding these ideas deeply. And then you should, when you've done that and you're ready, please move on to the next and final chemistry review video.